Ayush Patla and welcome back to Singular Science. Today, I want to talk about one of my favorite topics in chemistry, a phenomenon so powerful that it could power space exploration for millennia to come, or perhaps even destroy human civilization as we know it in a single day. I'm of course talking about radioactivity. But before we delve into that, we need to start small, atomically small. As you may recall from my previous video, atoms are composed of even smaller particles, the positive protons, negative electrons, and neutral neutrons, which are fittingly named subatomic particles. These particles are arranged in a certain way where the electrons orbit around the protons and the neutrons, which are found in the nucleus. It's also important to note that the number of electrons is equal to the number of protons, making an atom electrically neutral. This number also represents its atomic number on the periodic table. These particles dictate the properties of the substance. For example, changing the number of protons in an atom gives rise to a completely different element. If you add a proton to hydrogen, you'll get a helium atom. Similarly, adding a proton to helium gives you lithium. Meanwhile, if you change the number of neutrons, you will remain with the same element, but with a slight variation in their properties. These variations are called isotopes. These isotopes you see here are the isotopes of hydrogen. Sometimes isotopes have unstable nuclei, leading them to release radiation to become stable. These examples in front of you are some of the unstable isotopes. It's important to note some elements, like radon and radium, release radiation in their base form. These substances that release radiation to achieve stability are called radioactive substances, and the process of releasing radiation itself is called radioactive decay. To understand this more clearly, we must talk about how the nucleus exists in the first place. As you may already know, like charges repel each other. The same can also be said about like-charged particles, in this case, protons. So how does the nucleus stay together with nucleons being so close to each other? Well, the reason it stays together is the strong nuclear force. This force is much stronger than the electrostatic repulsion between protons, but it only acts over very short distances. At close range, the strong nuclear force binds protons and neutrons, collectively called nucleons, together, overcoming their natural repulsion. However, as nuclei become larger, the repulsive force between protons increases, while the strong force cannot reach across the entire nucleus. This imbalance can make large nuclei unstable. As a result, unstable nuclei undergo radioactive decay, releasing particles in order to become more stable. Now, this radiation can be released in three different ways: alpha decay, beta positive and beta negative, and gamma decay. Starting off with alpha decay, which releases 2 protons and 2 neutrons, which is essentially a helium nucleus. These particles are very bulky and can be stopped by a piece of paper. It's also the most common form of radiation. Moving on, we have beta decay. There are 2 types of beta decay: beta positive and beta negative. In beta positive, a proton converts into a neutron and releases a neutrino, and to even out the charge, a positron, a particle with the same mass as an electron but carrying a positive charge. In beta negative, a neutron turns into a proton and releases an electron and once again a neutrino. After alpha or beta decay occurs, the nucleus is left in an excited state. To return to a lower energy state, the nucleus ejects a highly energetic wave in the gamma range. This is gamma decay. This video just scratches the surface on this fascinating phenomenon. Next time, I hope we can also talk about the applications of radioactivity in our day-to-day lives. With that being said, thank you all for watching and see you next time.